Today we're going to continue our investigation of complex numbers. So we began by talking about what complex numbers were, with I being the square root of -1, which is that thing that puzzled people for a very long time. So today we're going to look at how you combine complex numbers in just the basic ways that you're used to. So what are ways we combine numbers that you've learned since you were a wee little child? Adding them, subtracting them, multiplying them, dividing them, raising them to powers. So we're going to see how to do that with I today, basically. And there's a couple neat applications in here, so we'll see some applications as well. Not in this video, but they'll be in the next one. Okay, so basic properties of complex numbers. So first, I'm going to graph some complex numbers. We need to think about a whole nother universe in order to actually graph complex numbers. So this is not the XY plane. Notice I don't have it labeled X and Y. This is the complex plane, which is one that you're not used to seeing. This is the first time you've ever thought about it. Because complex numbers, even though the I part is called the imaginary part of the number, it's really not imaginary. People called it imaginary just because they couldn't really see it really well with their eyes, just like when you look at electricity, most of the time you can't see it unless it's so intense like lightning. It's not really that they're imaginary, it's just that they kind of dwell in another dimension. Does that make sense? You guys have, I'm sure, seen science fiction movies where there's other dimensions where aliens live or whatever. Well, there's other dimensions where math lives too, okay? And those other dimensions control a lot of the reality that you experience. All electronics run on them, for instance. Well, not completely, but partially, yeah. So, this is another dimension, the complex plane of reality. If you're thinking about the complex plane, complex numbers are a plus b I. So they have a real part, and then if they're not strictly real, like everything you're used to till now, if they're not strictly imaginary, then they live somewhere in the combination of the two. So there's the real axis, and what do you think this axis is called? The imaginary axis, or the I axis, if you will. So, what is the coordinate of point A in the complex plane that I have graphed here? Richard? What do you got? Yeah, it's by twos.
So it'd be 8, real number 8, and then imaginary 0.
Yeah, exactly. So you write that as 8, and then if you wanted to put plus 0i, you could, but you don't need to put plus 0 stuff, right? Like, you don't do that in reality. So I'm not writing this as a coordinate, I'm writing it as a plus bi, which is kind of like a coordinate. So b, what are the coordinates of b? The real part is 4, so it's going to be 4. Yes, I hear a few people. 4 plus 3i. There you go. C. -8. Maybe I should make these spaced out a little more. C is going to be -8 plus 1i. D is right here, so that looks like 8, 10, 12. Hard to say, maybe -3 or -4. I'll say -3i. You guys got me? So, it's pretty simple. This guy doesn't even have a real part, it's just -5i. If you wanted to put 0 minus 5i, great, but it's not really necessary. And then F is going to be -10. I think I went -3i again. Depends on how straight I drew stuff, right? So there's the complex plane. It's not very hard to work with the complex plane, and we're not going to see it a huge amount in math unless you go beyond into electricity and physics pretty far in college, or in computer science, used pretty much a lot too. So adding or subtracting. So how do you add complex numbers together? Notice, how many complex numbers do I have there that I'm trying to add together? How many numbers? 2. There's really just 2 numbers there. Is there any real reason to have the parentheses on there? No, that was just so you guys could see that there's 2 complex numbers there. How do you add them together? Well, you can do that graphically, which I'm going to confirm in a second here. That part's kind of neat, but long. Doing it algebraically is super easy. You combine like terms, that's all. I mean, like you put the real parts together. What's the real combination here? -2. And the imaginary combination is -5i. So just like x's combine when they're like terms, so do i's and numbers. So when you add these two together, you get -2 minus 5i. I'm going to draw that on here so you can kind of see that on the complex plane. I think that's kind of neat. Let's get these other points kind of out of the way. Let's see, so let's plot those 2 points. 4 plus 2i, so that's 4 and 2i, so there's that one, right? And then we've got -6 minus 7i. Ooh, a -7 might be hard to graph on mine, let's see. So -6 is right here, minus 7i, so there's -5 about right here, yeah? So this isn't going to be perfect because I didn't draw perfectly, but I think you guys will get the picture. So to do this, you then draw lines from the number back to the origin. And where's -2 minus 5i? Let's plot that. So we wouldn't have that, but let's just see what this looks like. -2 is right here. Minus 5i is right here. Oh, my pictures are not the greatest here. Yeah, I'm going to do a different picture. Let's do that one with a different one. So I'll do that with a different picture. This one's going to be too hard to see. Let's do this guy. So combining like terms again. Can I just drop these parentheses like I could have dropped those? Mostly, but what do I have to do with this? I have to distribute it, right? So that's the only thing you got to be careful about. So I can say this parentheses set is not really necessary. This one I need to distribute. So I'm going to get +2 plus 3i. Now I can put it together. So I've got 7 plus I. Okay. So let me see if I can cook up an example that we can graph better. So let's do 3 minus I and 2 plus 3i. So 3 minus I plus 2 plus 3i. Let's try to graph that guy on here. And I'm going to change this from 2's to 1's just to make it nice and simple. Okay, so now this is at 4. Okay, so 3 minus I is 3 minus I. 2 plus 3i is 2 plus 3i. Draw lines back to the origin. What's the answer going to be on this one? You guys just help me out. Do it in our head, right? 5 plus 2i. Let's plot where 5 plus 2i is and see if we can see what the picture looks like. 1, 2, 3, 4, 5 plus 2i is right there. How does that relate to those other 2 blue segments? Let's pretend we didn't even know that. Yeah. If you draw another parallel side and you think about grabbing this and dragging it so its beginning point goes to this end point, so that in other words you form a parallelogram, that's what you do. This is the basis of vector math actually, so that's the only reason I'm showing it to you, because we'll use vectors later this year or next year. So if I take this and grab it and make a parallelogram by sliding it up and thinking about the addition of those 2 segments, that's where the addition of those 2 complex numbers comes from. If you wanted to subtract them, what would this be with subtraction? If I put a minus here, I've got to add some parentheses, right? So then this would be 3 minus I minus 2 minus 3i. Put those together and you get 1 minus 4i. So let's go back and graph that one. Okay, so now we've got 3 minus I, same spot, 3 minus I, there's that one again. 2 plus 3i is being subtracted. So there's that one. 2 plus 3i is right here again, right? But since it's being subtracted, I don't do this. I take its polar opposite and I subtract it and go down there, which is basically just this part, right? That's what this distributing gets you. It gets you down to -2. This is 2 now, right? You can see that I went down there. And now you put them together. So where's the combination going to be? We could just kind of eyeball it. Let's see. Eyeballing it, dragging this to here. Something like that, right? Is that maybe 1 minus 4i? It's not perfect because it's a drawing, right? But if I drew it perfectly on graph paper, it would be. So that's about 1, right? And it's about 1, 2, 3, 4. I'm off a little bit, but you guys get the picture. So there's what this actually kind of looks like with vector/polar math, which is stuff that we'll use a lot in the future. So a glimpse of the future. But adding and subtracting these, how easy is it? Do you have to do it with a picture? No, it's just like terms. So if you want to do it with a picture and a couple just to have some fun, explore on your creative side, I'd encourage that, but you don't have to. Okay? So let's look at, we added and subtracted them. Let's multiply and divide them, but before we multiply them, isn't it pretty likely that we're going to have 1i times another I? So what is I squared? I think we better figure out the powers of I first. So let's look at the powers of I. So powers of I think we're going to need this little wheel. So let's just start by thinking about I, what that is. We'll look at I squared and I cubed and I to the 4th and I to the 5th and all those different possibilities. It could be to any power, but I think we're going to find something. What is I again? It comes from the square root of -1. So I squared, couldn't I just write that twice? What happens when you do that? If you have the square root of 2 times the square root of 2, that's the square root of 4, which is 2. So this is the square root of -1 squared. What's squared do to square root?
Makes it disappear.
So I squared isn't square root of -1. It is -1. You can do that with any power and just keep going. This one we just learned is -1, and then we've got another square root of -1 here. But the square root of -1 is also known as I. So this is negative I. I to the 4th you could write out 4 times, right? It'd be long though. I'm running out of space. You guys see I'm going to hit my edge. I want to hit my edge. It's going to make things messy. So couldn't we also say that that's just like I squared? I squared? Yeah. And I squared each time is -1. So Kyle's saying negative times negative is +1. See, and then if we do I to the 5th, couldn't we write that as I cubed times I squared, or I squared times I cubed, or I to the 4th times I to the 1? We've got lots of options. Or we could just write it out 5 different times, right? There's all kinds of options. I think we should think about it like this, though. Because we just learned I to the 4th is 1. So in other words, that's I again. What do you think I to the 6th is going to be?
I to the 2nd.
It's going to be this if I write it out. I to the 7th will be
I to the 7th.
this. I to the 8th will be this because it's just 1 times 1. I's have a cyclical power nature. That's why my wheel up here has 4 steps. All powers of I are one of 4 things. Those 4 things are right there. If you have I to the 1 or any modulo of 1, then you get I, which is, we'll just remember the square root of -1. If you have the 2nd step, you get -1. If you have the 3rd step, you get -I. If you have the 4th step, you get 1, and since it's 1, the cycle starts all over again. So I to the 5th would be here, I to the 6th, I to the 7th, I to the 8th. You can count around this if you want to do things the slow way. But that's definitely something that works. So I is cyclical. How many steps? 4. You need to know all these steps, so they need to be memorized. I squared is the most common, but sometimes these guys come up as well in different combinations of complex numbers. Okay? So let's see some places that we might need that. So I wanted to multiply some complex numbers. I think we're going to need it there for one. Let's do these two problems. And then let's see what happens after that. We're also going to try to just do some higher powers, like I to the 24th and I to the 63rd and something like this. Okay, so first, some multiplication. You can see this is one complex number. It's just imaginary, but that's still complex, times another one. So we should get one answer, one complex number, one a plus bi that comes out when we do it. But this doesn't work like stuff that's totally new. I mean, it works like stuff you've always known how to do. How do you do this kind of problem? Distribute, right? Like, it's not like this is so different than other math that you've learned. So this is going to be negative 4i, right? And that times that, negative times negative is positive, 8. We've got I times I, which is I squared. Are we done at that point? Well, no, because this doesn't say a plus bi. It says I, and then it has an I squared thing. I squared is negative 1. So this is really negative 4i plus 8 times negative 1. If I write that the correct way, it's negative 8 minus 4i, a plus bi. One number times another number is one number. That's the kind of thing you should have on pretty much every problem that you do, no matter how complex it is in this section and in complex mathematics. Okay? So this guy, how do I do it when you've got like multiple pieces? There's a word called FOIL. I'm not fond of it, but you expand, right? It's just distributing again, except you got to make sure you get everything times everything. So you could go like this times this, so that's 12 minus 3i, and then you could go this times this, which is 24i, positive 24i, minus 6i squared. Any like terms in there? Well, yeah. We've got 12. These are together. 24 minus 3 is 21. And these are really like terms too. You guys are like, what? That one's I squared. This one's just 12. But I squared is negative 1. So this is negative 6 times negative 1, which is 6. And 12 and 6 is 18. One number times one number is one number. I know they have two parts, but that's one number. Complex numbers have real and imaginary parts, unless one of those is 0. Okay. Why don't you guys try, well, let's do some powers first, and then I'll give you guys a couple to try on your own. So I to the 24th power. What's that going to be? You can count it. You can go up to your wheel here. Why, by the way, did I do this like counterclockwise? So it matches something else that you know.
Coordinate grid.
Yeah, because quadrant 1, 2, 3, 4, just so it's consistent with other stuff. Do you have to do it that way? No. Okay, so 1, 2, 3, 4, 5, 6. You can count all day. Where am I going to land, though, if I'm counting to the 24th power? On the 4. So that's going to be what? 1. I to the 63rd, you're like, man, I don't want to count that high. Mr. Garner's saying it's divisible by 3. What's he mean? Means that 3 divides into it. That's one way to think about it. I like to think about it like this. So I'm just going to, but he's right. What's the closest power of 4 underneath? 60. That's above. Closest power underneath is 60, right? So you could write this as all kinds of combinations, just like we were thinking about a second ago. That's a really good one though, because I to the 60th is 4 goes into it, it's divisible by 4, and all powers of 4 are the easiest. They're just 1. So this is really just 1 times I cubed, and I cubed is something you got to memorize or come up with again by doing that little thing right there. So that's going to just be negative I, because it's 1 times negative I. Okay? But Josh's way was right too, because he divided by 3. He said it's going to be on the 3rd step, which it is. Very nice. Okay, 14, you could count that one easy, but think about it like this, and you don't have to write this out, by the way. It's good to write it out, I think, but it's not absolutely necessary. 14th is going to land where? Where's the closest power of 4? 12. So that's 1. And how many steps forward do we have to go from 12 to get to 14? 2. So instead of being I, it's going to be I squared, which is negative 1. And that one you're going to use so much you don't even have to try to memorize it. So this is going to be negative 1. So we have negative 6 times negative 1, which is positive 6. All right, here's a couple for you guys to try just to see if you're getting the hang of it. So a couple more. Let's try multiplying 3 minus 2i times 7 plus 6i. Let's do that one. And then let's try a couple powers. Let's go I to the 87th. And let's go a little combination here. Let's say we had 5i to the 9th minus 3i to the 27th. So if you're watching the video, I'd pause it and try these right now before moving on. Okay, so just so you can check your work on these guys, here's what you should have gotten. 21 and 18i, and then we've got negative 14i and negative 12i squared. But I squared is really just negative 1, so you can show your work if you want to. I'm not going to this time. This is then positive 12, isn't it? Because it's negative 12 times negative 1, 12, and 21 is 33. 18 minus 14 is 4. That's the correct answer on that one. Okay? So these guys, you can do all kinds of different ways. I don't want to count on my wheel for 87 because, like, man, that'd take a while. So I'm going to say, well, what's the closest multiple of 4? I think it's 84. So I'm either going to write or think like this. I think it's best to write it down, even if you can do it in your head. That's useful later on when things get tougher. Any power of 4 is equal to 1. So I really don't even need that part. Any power of 3 is equal to negative I. So this is negative I. Okay, down here I'm just going to do it for each piece separately. So I to the 9th, you could count. You could go 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's just I, or in this case, 5I. 27, also feasible to count. I'm just going to think about this one in my head. 27 is close to 24. 24 is 1. 25 is negative 1. 26 is negative, well, did I skip one? See, I'm being dangerous here. So 24 would be right here. I skipped one. 25 would be right here. 26 would be right here. 27 would be right there. Okay, so this is negative I. So that's negative times negative is positive. So I have 5i plus 3i. That's 8i. Okay? Let's look at dividing complex numbers. That will be good with basic properties of them. So there we go. So dividing complex numbers. Let's look at this one. And then let's do this one too. I'm going to go a little quick just so we can get done. Go back and watch it again if you're confused while you're doing your homework, yes? Okay, so how do you divide complex numbers? Well, you have to use something about complex numbers we kind of already knew about, which was if you use them to solve it, I mean, if they come up in the course of solving a parabola, how many are there? There's always two. There's always a conjugate pair. That conjugate thing is useful for all kinds of things in mathematics. It's one of the ways, for instance, that we divide i's, because otherwise we couldn't divide i's. So I'm going to multiply by a clever one. The clever one that's most useful in imaginary land is the conjugate. It's useful for all kinds of things. What's the conjugate of the bottom? Negative 5i. If I do it on the bottom, I got to do it on the top. That's that property of 1, the clever one that makes it legal, yeah? Because I could just like chop that off if I wanted to, and it'd be back to what it was. Okay, why is that useful? Well, because on the bottom we're now going to have negative 25i squared. On the top I need to distribute it, right? So I'm going to have negative 15i minus 50i squared. And I can simplify this by, of course, remembering that I squared is also what? I to the fourth is 1. I squared is negative 1. So I've got negative 1 times negative 50 is positive 50. Negative 1 times negative 25 is 25. That's really just a complex number in disguise. You're done if you see it. What's 50 over 25? 2. There's the real part. What's 15 over 25? Well, we might not be sure, so we can just write it down. It's negative, right? Negative 15 over 25i. You see the a plus bi? There it is. So it's 2 really minus 3/5 I. A plus bi. One complex number divided by another complex number, as you can see here in black, is that answer. Okay? That's the way all your problems should work. Let's do it with one that takes a little bit more work. So I'm going to do the same approach here. Multiply by the conjugate of the bottom. What is the conjugate of the bottom? 4 plus 2i. Yes, sir. If you do it on the bottom, you got to do it on the top. And then you just see what happens. This is a little long because you got to FOIL them both out, right? So how many things am I going to get on top, though, at first? 4. And how many on the bottom? 4. So here comes the 4. 2 times 4 is 8. 2 times 2i is 4i. 8i times 4 is 32i. Then we've got 16i squared. Watch out for your I squared. Students I've had in the past often leave out the I squared. That's where they make mistakes, I think, usually. Then do the same thing on the bottom. So we've got 16 plus 8i minus 8i. No, this part's the tricky part. Be careful here. Minus 4i squared. The whole reason we use conjugates to do this, one of the reasons, is conjugates do nice things. What did they do on the bottom? They got rid of these parts. That's what's special about the conjugate, one of the reasons. And then we know about I squareds, right? So this is really just negative 1, right? So negative 4 times negative 1 is 4. 4 and 16 is 20. Now there's no more i's on the bottom. That's why this works. The conjugate basically gets rid of all the I stuff because the cross terms go away, and the I squared you can just change into negative 1. That's why this works. On top we can do it as well, so this guy is also negative 1. So I have 8 minus 16. If you want to write out another step, you can, but I mean, it takes a while then, so it's up to you. You can do a little scratch work up here. You could be like 8 plus 16 times negative 1. That's 8 minus 16. That's negative 8. If that floats your boat, then do it. Then we got some like terms here, 36i. Whether or not you recognize it, that is the answer. It just doesn't look good yet. The real part is this. The imaginary part is this. So I've got negative 8/20ths plus 36/20ths I. Those, I think, can be reduced. 4 goes into that twice, and into that 5 times, and into that 9 times, and into that 5 times. A plus BI. One number divided by one number is one number. I'll see you next time.